This video is going to cover the most basic definition for the entire course, which is what is a vector and what is a vector space. So we're going to do vector spaces, and sort of everything we do will be in the context of some kind of vector space, essentially. And with vector spaces, we're going to cover what is a subspace. That's an important idea. A subspace. And then the question that we're going to ask ourselves is, how do you do limits of vectors? So that's going to be the next thing. Limits of vectors. And that is going to bring us into the idea of norms. So those are the big important definitions. What is a vector space and what is a norm? And together they make something called a normed vector space. That's what we want to get to. So to start with, what is a vector space? I found this beautiful meme online. The definition of a vector space according to different populations of people. So there's computer scientists who say it's an array. This is the kind of thing you learn in linear algebra class, especially if you took a really mechanical linear algebra class that was all about calculating things. So you'd say a vector space. Well, what is a vector? A vector is little numbers like this. So you have like x1, x2, x3, and x4. That is a vector, and the vector space is all the possible arrays you can make of length 4. Now, the problem with this definition is it's an array. This kind of breaks if it's infinite dimensional, and that is essentially what we want to study in this class. So this is bad for infinite dimensions, and that's why we don't want to do it. Physicists say a vector is a quantity with magnitude and direction. And again, this is very practically speaking, like this is what the physicists do, right? They're saying we want to think of these quantities that you cannot represent as a single number, right? And instead of thinking of a single number, which is just, how much of something there is, we want to also take into account the direction. So this is very practical as well. But the problem is the direction bit sort of doesn't, once you get to infinite dimensions, it doesn't match your intuition anymore. So this kind of, I think, is this is like practical in physics, and this is like what we want to use them for. So I would say this is a good application focused definition. Right? It's like I want to be able to talk about things that have a direction, so I make this definition of a vector is a thing with magnitude and direction, and then I can unlock all sorts of things like adding them together and stuff like that. It turns out for us, we want this third definition, which is very blurry over here, but we will go into in more details. It's an element of a vector space. What is a vector? It's an element of a vector space, which is a set of objects that follow certain closure properties and axioms under vector addition and scalar multiplication. So this is extremely abstract. Why on earth are we doing this? Why don't we have a simple definition like this? The reason we do something like this is because if this is the definition, almost anything that we are interested in can be a vector space. Almost anything can be a vector space. So this is the reason the definition is the way it is so that really abstract things we can fit into the context of a vector space as long as we have this really abstract definition. By doing that, you sort of strip away all the things you don't need and you focus only on like what is the soul of a vector? What is the like absolute minimum you would need? And that is what we do. So we kind of trade, we pay the price of having to work abstractly, but we gain generality. We can be very general, and we're going to see all sorts of really weird and wonky vector spaces in this course. Crazy vector spaces with lots of weird functions and lots of counterintuitive stuff in them. So that is the reason it is going to be the way it is. I will say, here's another meme I found that I really liked, which is the definition of a vector space. So vector is an element of a vector space, but what is a vector space? A vector space is a set whose elements are vectors. So the vector space really is the collection of all the vectors. The vector space equals the set of all the vectors. So this definition is kind of circular. So the real actual definition that I'm going to get to in a minute, straight from the textbook, is I'm going to give you the informal definition first. What is a vector? What is a vector? What is a vector? And the answer is vectors are things that you can add to other vectors and things that you can scalar multiply. So answer. So a vector is something that you can scalar multiply and add to other vectors. Is something you can one, add to other vectors. I'll say add, subtract, because very often we subtract them to other vectors. Okay, going a little bit on a slant here. Let's try to keep it straight. And the other thing you can do is you can scalar multiply it. And scalar multiply means multiply it by, for example, if the real numbers are the scalars you're using, e.g. r scalars, then you can multiply your vector by a half or multiply it by 2. You can shrink and stretch the size of vectors by multiplying them by numbers. Okay, this is very important. That you don't, you can't. These are the only two operations. You can't do things like multiply two vectors, for example. You can only stretch and scale them by real numbers, and you can add and subtract them from each other. This is the most general definition that still does all the things that we want. To be very technically precise, you need a third thing, which is, you can, what does can mean? Can, in a way that obeys all the basic rules that you would expect things to do. And that is what is recorded in the textbook. So the definition has a very technical definition that is saying, what exactly does it mean that we can add and subtract, and we can scalar multiply? So we have these two operations. One is called addition. This really should be called vector addition, right? Because it's what we're doing is we're taking two elements from E. E is the vector space. And we are saying it makes sense to do x plus y. You get a new vector. So you input two vectors, something in E, something else in E, and you output something in E. So x plus y is its own new vector. X plus y is a new vector. A new vector because it's in E. So you have this vector addition operation. You have this scalar operation. So if you do lambda times x, lambda has to be from the field f. In our class, f will always be either the real numbers or the complex numbers. So f is a field, and it's either r or c in this class, but in other courses, it might be something else. And so you have these two operations, vector addition and scalar multiplication, multiplication by scalars, and they have to obey the following sort of sanity rules, right? So you have these two operations, and they must obey these kinds of very basic operations. For example, you would want that x plus y equals y plus x. The order doesn't matter. You can add things up in any order, and you get the same final answer. The other thing you can do is distribute in any order. So you can add up x plus y first, and then add z. Or you can add y plus z first, and then add x. You should get the same final answer. I'll come back to this one. This one's a little funny. I will come back to this one. This one is the same kind of rule, doing things in any order, but for scalar multiplication. So if you first multiply a vector by some constant beta, so they're using Greek letters here, beta, alpha, and beta for scalars, and they're using x, y, z for the vectors in E. And they're saying, if you multiply first by beta and then by alpha, so first stretch a vector by beta, then stretch it by alpha, that's the same as multiplying alpha and beta together as numbers and then stretching x. So very, very basic, like what you would expect on how scalar multiplication should work. This property and this property, they say that vector addition and scalar multiplication play nice with each other. So these properties say that you can't just have any old vector addition and scalar multiplication. They have to be compatible. So this says vector addition and scalar multiplication are compatible. And compatible here means that you can just do this kind of distributive law that you would expect. And so that must work for the things you gave me. Finally, this is a very funny property. If you multiply a vector by 1, it doesn't change. So 1 times something has to be the original something. This is just saying, the number 1 is an important number, because when you multiply numbers by 1, nothing changes. That has to work for vectors as well. Okay, last but not least, let's go back to this one that I skipped over. This one is a very, very weird one, because it's a there exists property. So it's saying you give me x and y, and I can find there exists a z such that x plus z equals y. And another way to say this, if x plus y equals z, you would very reasonably, if x plus y equals z, you would very reasonably argue that z is actually the vector y minus x. And what this is saying is there is some vector that is the difference of y minus x, and that vector, you can define it this way. I personally find this a very extremely weird, terse way to define this thing. This is just the textbook we're using. They have this weird definition. I think this in some sense, these definitions A through G given this way are the absolute minimum definitions. That, like if you were like, let's save paper and write down the shortest possible definition of a vector space, this is what you would write. If it was me, I would just say, it's okay to subtract vectors, and subtraction plays nice with addition. So some other people will write things like -1 times x. That is a vector called -x. And in fact, the textbook, a few pages later, they have these properties, and they're like, the following properties can be they follow easily from the definition of a vector space. This is a few pages later, and they say 0 times x equals 0, and -1 times x equals -x. So this idea of adding vectors to get the negative, you can get it through scalar multiplication as well. If it was me, I would have just put this in the definition. I don't know why they wanted to do this, but this is like a common theme in technical mathematics, is that people write down the shortest possible definition, and that kind of makes it harder to understand sometimes, but it does make it sort of more technically compact, and like it strengthens the sort of the ease of the proof sometimes, at the level at the cost of sometimes having less understanding. So I would just take these as part of the definition. That would be fine to me. You put those in the definition, you make the definition a little bit longer, and then you don't need these funny like there exist statements. But essentially, this is the technical, the legalese, the fine print for the thing I said before. Well, what is a vector? A vector is something that you can add and subtract with other vectors. So addition makes sense, and you can scalar multiply it. And that is what a vector is. What is a vector space? It's all the possible vectors, the things that you're adding and subtracting together. So maybe that makes this a little bit less scary, but maybe you're also like SpongeBob and are still quite confused. Let's do some examples. I think this is the best thing to understand. Okay, first example, the set 0 is a vector space. This is a terrible example. Let's just skip this one. This is very confusing. You're like trying to, technically the 0 on its own satisfies all these things, but sort of in a very vacuous, silly way. The scalar fields R is the simplest non-trivial vector space. This is again kind of confusing because I said vectors are things you can add, right? So let's see what we can do. We can add and subtract other vectors. So if we're thinking of vectors as R, can we add and subtract elements of R, real numbers, to each other? Well, yeah, we can. So yeah, R is good for adding and subtracting. R, you can also scalar multiply. But the thing you're scalar multiplying with is R itself. So now you sort of have two, you have to keep R in your head twice. R is the vectors, but also the scalars. And that's a little bit confusing. So I don't like this example either. So I'm going to cross this one out as well. And let's say that our first example is actually this first example, which is the one you do in linear algebra class. So you fix some capital N. Let's say, for example, n equals 4. And then we would have R4, which are 4 tuples. So x1, x2, x3, x4, in such that all the elements are in R. x1, x2, x3, x4. And I would say, another way you could write these is like vectors like this, like I did before, x3, x4. And the rule is you add them together entry-wise. So R4 with entry-wise, addition, scalar multiplication. So if you want to do x1 plus x2 plus x3 plus x4, sorry, you take the vector x1, x2, x3, x4, and you add on y1, y2, y3, y4, you're going to get what you think you get, which is the sum of all these is a new vector where you add the individual entries. x2 plus y2, x3 plus y3, and last but not least, x4 plus y4. Okay. I have another more complicated example coming soon. Don't peek. x4 plus y4. Okay, beautiful. So that's addition, and scalar multiplication works the same way. So if you were going to multiply the whole vector by lambda, you would multiply each individual entry by lambda. So this rule, that is kind of obvious to you from linear algebra class, we now have to define it. We say that is the definition of the addition and scalar multiplication. And then you have to go back, technically you would have to check, does it satisfy all these properties? Is it true that x plus y plus z is the same as x plus y plus z? And you would have to check that it's true. In this case, it's not complicated because we know it does that in every single entry, and we're doing this entry-wise thing, so everything will follow from the fact that all the properties hold for every individual entry, which is why, they said R is a vector space. When R is a vector space and you stack together 4 copies of R with this entry-wise thing, it's still going to work. Okay, so that's a very sort of boring example. There's a more exciting example over here. Before I do the more exciting example and before I say what a subspace is, let's do a couple more examples that I have written down. So we had examples of vector space, of vector spaces. We had R4, and in general, you can have R to the n for fixed n, right? Any R to the 100, R to the 100 million, it's all fine. But here's an interesting one. If I'm going to be sort of naughty, let me write R to the infinity. R to the infinity. What is R to the infinity? Well, you just don't stop. So you go x1, x2, x3, ... And there is no end. It's sort of a vector that goes on forever. And as long as we do the entry-wise addition and scalar multiplication, this will still work as a vector space. So very technically speaking, so xi is in R for each I. And then we define this with ordinary entry-wise addition scalar multiplication. Okay, lovely. This still works. This is kind of a nasty space. It's sort of infinite. It just goes on forever and ever. We're going to see that this space is sort of too unruly to work with, and we're going to find ways to sort of tame it and work with kind of like versions of this that are a little bit nicer. I'm going to get to that in a minute. But technically, this is a totally valid vector space. You can add and subtract things. You can scalar multiply things. Everything still works. You're going to see later on some of the things we want to do will break, and we're going to have to sort of rescue this by doing some stuff. But that's a good example. This is an infinite dimensional space. So these ones are finite dimensional. And so this is our first example. So if you took an algebra class, you know that the dimension is something about the size of the basis and so on. I'm not going to get into it here. This one is not finite dimensional. There is no finite set of vectors that can span the entire space. So this is not finite dimensional. The next example I want to do is the space of polynomials. Polynomials. So what is this? Let's call this p of x. So I'm saying I'm using the variable x, and I'm doing all the polynomials in the variable x. So this is all the possible polynomials. What is a polynomial? Let me write out some. So you could have the 1, that's a polynomial. You could have x squared plus 7x plus 2, that's a polynomial. And I want to write out all the possible polynomials. What are they technically? Let's write it over here. It's the set of all things of the form x to the k times a k, and k goes from 0 to capital N for some n. So it's a sum of these terms with coefficients. I'm sure you know polynomials. So here n is some natural number, and ak's are in R. So it's got some highest degree I called n, and the ak's are in R. Oh, maybe I should say an should not equal 0, because if you make the very top term 0, then you can write a polynomial in more than one way. That way, the top term is not 0. So for example, this is a degree 2 polynomial because it starts with x squared. So the set of all polynomials, this is also infinite dimensional. So this is not finite dimensional, once again, because you can make the power as high as you want. Not finite dimensional. And this is our first example of sort of a space that doesn't immediately look like sequences of numbers. So this r to the infinity really is like sequences. The first component, the second component, it comes in a natural order. And when I write out the polynomials, maybe it's not completely obvious what the sequences are. But if you stare at it for a little bit longer, you can kind of convince yourself, hey, maybe there is a sequence actually under there. That's an exciting thing. Do all vector spaces have a sequence that you can attach to them? We're going to find out later in the course. So for now, polynomials. And I will say polynomials, when you add them together, you can add them together sort of entry-wise. You can add together the coefficients, or you could just say, think of the functions and add them together. So you could add a polynomial p of x plus q of x. This is a new polynomial. So adding together two polynomials is a new polynomial, and that is why the addition property, vector addition, is really adding together two functions. Okay, and you can also scalar multiply. So let me do multiply by some scalar lambda. You can also multiply a polynomial by 2, and it's still a polynomial. So this is all great. So this is a new polynomial, and you must check. Technically you must check. All the vector space axioms. Okay. In fact, this polynomial definition is a very nice definition. There is a even more general definition that looks a lot like this, and that is from the textbook. That is example 1.2.3, which is called function spaces. So anytime you have a collection of functions, just like I had with the polynomials, that was a collection of functions, that will be a vector space. And the rule is when you do addition of the functions, you make a new function, which is the sum of the old functions. So a set of functions, f, so f is the set of functions from x into e. So x here is just an index set, sort of an index set. And e, this is the output of the thing. Let me do a special example of, let's make the output set just r to make it a little bit simple. R. So this is the output. So if you have functions that are r valued, so the output thing's in r, then you have this really simple formula for adding together functions, which is if I want to add together the two functions f and g, then I should add f of x with g of x to evaluate f plus g at x. Very simple. It's like what you would expect. Same with scalar multiplication. And this will satisfy the rules of the vector space. This is what basically this example is saying, is that you can make these things. And everything will work because addition and scalar multiplication work in R in the output space. So if addition and scalar multiplication work in the output space, then you can make functions of that thing and it will still be a vector space. You might think this is extremely abstract, but we've actually already done examples of this. All these examples that we've done are secretly function spaces. Maybe the hardest one to see, it's a function space, is the simplest one. In what way is r to the 4 a function space? Well, it's a function. You can think of a vector in r to the 4. So x1, x2, x3, x4, that's a vector. You can think of it as a function that inputs either 1 or 2 or 3 or 4. So normally you would say this is a vector. It's equal to this thing. But you could also think of it as you have x, and you have this operation of you give me an index, either 1 or 2 or 3 or 4, and I will tell you a real number. Okay? So you give me a number, 1 or 2 or 3 or 4, and I will tell you back one single real number. And what is it? X of I is the ith component xi. You see? So instead of thinking of it as a list of numbers, think of it as a list of outputs. And then it's a function. And then the definition we just did is actually, it's a function space. The index set here is just this very silly set with 4 elements. So this is the index set of 4 elements. Okay, that's very nice. What about this other one? I did r to the infinity. This was, again, a function space where the index set is now the natural number. So actually it would have been more honest to say this is r to the power n. And really, these are functions. Everything in r to the power n is a function. I called them x again. So it's x, and it inputs a natural number and outputs a real number. And if you give me the natural number I output the ith thing on the list, xi. These are also called sequences. Sequences, so n valued, n indexed sequences. Sequences. So this is a sort of sequence space, and it's just a different way of thinking about it, right? So instead of thinking about a vector where the components go on forever and ever, think about the inputs as which entry you want to look at, right? So this is the natural numbers are the input. So for example, if I input 3, you output the third entry, x3. Polynomials, this one, I said it was an abstract space of functions, and you can think of any interval you want for what is the allowed x values. So for example, you could say x is in 0, 1, and then you can think of p of x, so some polynomial p of x is a function p that inputs a number between 0 and 1 and outputs a real number, and it's a polynomial. So you are allowed to make these x inputs anything you want, and p is a polynomial that inputs anything in that 0, 1. So actually in this course, almost everything will be a function space. So this sort of definition will be the holy grail for us. Everything will be a function space, and so it's important to think of what are the outputs, what are the inputs, and remember what is the scalar multiplication and addition, because this scalar and multiplication and addition will be used everywhere. So it's a good one to keep in mind. Okay, the next thing I wrote to show you is what is a subspace, which is not covered in the textbook. So let me write what is a subspace. A subspace. So a subspace is a chunk of a vector space that is a valid vector space on its own. So S is a subset, I'm going to call it V. If V is a vector space, V a vector space. S subset V is a subspace, means S is a valid vector space on its own. On its own, using the addition and scalar multiplication from V. So say vector addition and scalar multiplication from V. So in other words, V is a vector space. It comes with an addition and a scalar multiplication. If you have some subset of it, you still have an operation, a vector addition and a scalar multiplication. It works for every single thing inside of V, so therefore it works for every single thing inside of S. And what we're saying is we're going to call it a subspace. If S on its own, if you deleted everything outside of S, then it would still be a valid vector space. And I think the easiest way to see what's going on here is with an example. Let's do an example. And the example, you can look at the space of all possible functions. So let's take all functions f from 0, 1 to r. These are all functions from 0, 1 to r. And we can look at the space of polynomials. That's the p on 0, 1, which we said is polynomials from 0, 1 to r that I defined earlier. So it has to be written as a sum of coefficients with powers of x. And every single polynomial is a type of function. Polynomials are a subset of all the possible functions. And the functions on their own are a valid vector space. That was the function space we defined in definition or example 1.2.3, right? You can add them together and scalar multiply them. Totally valid vector space. And the polynomials, as we saw before, they are also a totally valid vector space with the same scalar multiplication and addition. And so the polynomials are a subspace. Therefore, polynomials are a subspace. Polynomials are a subspace of all possible functions. A subspace of all functions. So it's a vector subspace. And in practice, I gave the definition over here. This was my definition of a subspace. I said it is a vector space, but in practice, you just have to check two things. And so this is kind of like a proposition or a lemma. Let's call it a lemma. A lemma. Let's call it the subspace lemma. That's cool to give things names. The subspace lemma. And the only things you have to check are that the subspace is closed under addition and multiplication. So if S is closed under addition, vector addition and multiplication and scalar multiplication. Oh, and there's one other thing you need, which is that it must contain 0. Technically, containing 0 is contained under scalar multiplication, because if you multiply by the scalar 0, you get 0. But I will write it out in full. So if S is closed under vector addition and scalar multiplication and has the 0 vector, the 0 vector is in S, then S is a subspace. Okay, and you might be asking, what does closed mean? Closed means if you do an operation, you stay inside of S. So closed under vector addition, closed. Let's say closed under vector addition means if, let's call them x and y. If x is in S and y is in S, then x plus y is still in S. So in other words, you cannot escape the space S by doing addition. When you do addition, if the two things you started with were in S, the thing you end up with is also in S. And it's the same thing with closed under scalar multiplication. Okay, so if x is in S and lambda is any scalar, I'll just say it's an R. In general, it would be an F. Then lambda x is also in S. So you cannot escape the space S by addition or scalar multiplication. The classic example of this is if you have something like R3. So if you have a three-dimensional space and you look at some plane in three-dimensional space. So you have to imagine you have 3D space over here, and you take something flat, maybe like a board or something, some flat board, and you hold it up in space. Then the set of vectors that are inside that board, those are a subspace. And that is because if you add two vectors that are in the plane, if you take two vectors that are in the plane, then you will get a new vector in the plane when you add them together. And if you shrink a vector that is in the plane and you shrink it down, it's still in the plane. So that's the classic sort of example of subspace in 3D and 2D. But in general, we're going to be looking at it sort of this way. And the reason this example works is because a sum of polynomials is still a polynomial. And if you scalar multiply a polynomial, it is still a polynomial. Okay, that is it for the very basics of what is a vector space and what is a subspace, with some very nice first examples. The other thing that we're going to need in this course is not just a vector space. We're going to need a vector space with a little bit of extra structure so that we can talk about limits of vector spaces. So convergence in vector spaces. And by this I mean we're going to have sequences of vectors. So we're going to have not just one vector, but a whole sequence of vectors, v1, v2, v3, ... a whole bunch of vectors. And we want to make sense of what is the limit as n goes to infinity of the vectors of Vn, right? And the thing that makes this hard is we have to do this in our vector space. So the v's might be some very, very complicated, weirdo, crazy functions or something, and we want to make sense of what this limit means. To start with, we're going to review what is the limit, the ordinary limit. So this is like review of the ordinary limit of sequences. The ordinary limit. And so very roughly speaking, if you have numbers, right? What should I use for numbers? Let's call them x's. x1, x2, x3, and so on. And do watch out because the textbook, and I will also be using x's to mean vectors, but here they mean numbers. So these are the xi, let's say, is a sequence of real numbers, subset r. As a bunch of numbers. What does it mean for the limit as n goes to infinity of the xn's to be some limit? Let's call the limit L for limit. What does that mean? Well, roughly speaking, it means the x's get arbitrarily close to L. And so this is the key thing, the key idea that we're going to take into vector spaces is the sequence, the limit is L, means the sequence is getting closer and closer and closer and closer to L. How close does it get? It gets arbitrarily close. And the way we phrase this mathematically, the technical definition is we use an epsilon and an n. So we say the limit is L means, so the limit is L if and only if, this saying the limit is L means for any epsilon greater than 0, we can get within epsilon. Let's put this in quotes again. This is going to be another layer of informal. The xn's eventually get within epsilon of L. Okay, and what does that actually mean? What does that mean? Again, so that's another layer of informality, and the true formal definition is for any epsilon greater than 0, the xn's, let's say this way, there's a some value, so I'm going to put there exists some capital N such that if n is greater than n, and this is some natural number, some index, then the absolute value, let's put it down here, the absolute value of xn minus L is less than epsilon. Okay, so the distance is within, we are within epsilon of L. This is the idea we want, within epsilon of L. And the way we do that is we use the absolute value. So the absolute value of xn minus L has to be less than epsilon. Okay, and this is the idea that we will take away to our vector spaces. So taking our, what does it mean for a sequence to converge in R, right, for an R value sequence? We're going to generalize it to vector spaces. So we're going to have sequences of vectors, and it's going to be the exact same idea. They are going to get arbitrarily close to something. That something will be a vector, not a number. And what does getting arbitrarily close mean? It means we get within epsilon of it. And what does getting within epsilon of it? It means something exactly like this. But the thing is, we can't do absolute value. So the absolute value function, right, measures distances in R. If you have a ruler and you measure what is the distance between the number 4 and the number -5, well, you take the absolute value of the difference, and that is 9. And that is what we did in our formula, but we can't use the absolute value on vectors, because what does the absolute value even mean? So if we have these crazy vectors like we had in the first half of the lecture, then what does it mean to do the absolute value? And so we're going to generalize the absolute value function to something called a norm. So convergence in vector spaces, this is measured with norms, with a norm. And so the norm is just a generalization of the absolute value function, so that when we plop in the absolute value function, we replace it with a norm in this line of the thing, everything still makes sense. Everything is intuitively the same. And so the norm has to generalize the absolute value function. Here is the definition from the textbook. The norm, this is a generalization of the absolute value function on R. And it works, instead of working just on R, for some vector space. Okay. So you have some vector space, and you define this thing called a norm on it, and then you can do anything you would do with the absolute value function, you can do on your vector space. And the thing we actually care about is doing limits. Okay, what does it have to satisfy? These are the properties that it has to satisfy. So if the norm is 0, then it must be the 0 vector, right? And remember, the 0 vector is special because the 0 vector has the property that if you add it on to any other vector, that vector doesn't change. So this 0 over here is the 0 vector. If they were nice, they would have written a little vector sign over top of it. And the 0 vector is the vector for which 0 plus x equals x for all x, right? That's the 0 vector. So it's a very special vector, the do nothing vector. And what we're saying is if the norm is 0, it must be the 0 vector. And this is like super crucial. We're going to use this all the time. The next thing says it has to be what I call positive homogeneous. So I'll sometimes say that. Homogeneous just means it respects scaling. So if you multiply all the vectors by 2, all the distances should also get multiplied by 2. And it's positive here because if you multiply everything by -2, all the distances will also get scaled by 2, right? So sort of the negative sign will just change the orientation, but won't change the distances. So it respects scaling. That is a property that we want our norms to have. Last but not least, this is an important one. This is the triangle inequality. And there's a little, they don't call it the triangle inequality here, they call it the triangle inequality just underneath. Why is it called the triangle inequality? The reason this is called the triangle inequality is because of the following picture. So you make a triangle here. I'm going to draw x over here, I'm going to draw y over here, and I'm going to put them in this funny orientation, tip to tail like that. And the reason I'm going to do that is so that the vector x plus y appears here, x plus y. And so this makes a triangle. We have a triangle sort of whose one side is represented by the vector x, one side is represented by the vector y, and the third side is the vector x plus y. And the triangle inequality says if you sum up two sides of a triangle, it must be larger than the third side of the triangle. And that's exactly what this is saying over here. So if you take the length of this vector measured by the norm, that's the norm of x. You take the length of this vector measured by the norm, that's the norm of x. Oh, I said y. I said x before, but I meant y. The norm of y, the norm of x, you add them together, that is adding up this sort of two sides of the triangle. That has to be more distance than x plus y, which is the pink side over there, the third side. So it always has to be shorter to go directly along the pink side than to take a detour where you go off on some way. That's the triangle inequality, and it sort of says, you know, it makes sense to our intuition of distance. This kind of triangle inequality is used all the time in the argument, so you will get good at using the triangle inequality. If you've seen it in a metric space, you'll remember there's some notion of triangle inequality with metric spaces. I won't repeat it here, but the metric space, when you have just a distance function, also respects this kind of thing. The relationship between metrics and norms is simply that if you take the difference between two vectors, you do y minus x, and take the norm, that will be a metric. So if you want to translate it in terms of metric spaces, that is totally fine. You are more than welcome to do that. In the textbook, they have this extra observation that by some argument, you can prove that x has to be greater than or equal to 0. I would just add this again. I would add this as a condition. So the norm of x has to be greater than or equal to 0, always holds. So the length of something can't be a negative number. It's always at least 0. And if it's exactly 0, it must be the 0 vector. I would just add that as a condition. They have some argument here of why is true. They also have the inverse, the reverse triangle inequality. That is, they say it is used often. I think it's used sometimes. I wouldn't say often. So the main things to know, triangle inequality, the greater than 0. And most importantly, that is just a generalization of the absolute value function. If you've gotten used to using the absolute value function in your analysis classes, or the distance function in metric spaces, you should have no problem sort of translating over to the norm. It's exactly the same thing. And indeed, the thing we want to do, the reason we have norms is so we can make limits. We want to talk about limits. And so limits are the next thing I'm going to show you. That's the next definition in the textbook that we're going to do. Definition 1.3.6, which is convergence in a normed space. So normed space stands for vector space with a norm. Vector space with some norm, a norm, right? So it satisfies all the vector properties, all the axioms, plus it has a norm, and the norm satisfies all the norm properties. And the definition is exactly what I wrote before. So we have a norm space. The norm space consists of E, the set of all the vectors, and this norm function, which they write here. They write 2 lines and a dot to mean it's the lines. You can apply it to any vector. And we have a sequence of elements, xn. N here goes from 1 to infinity. So a sequence of vectors labeled with x. It converges to some x. So we're saying, what does it mean for the limit as n goes to infinity of xn to equal x? What does that mean? And once again, the idea is the xn's are getting arbitrarily close to the x's. Arbitrary close means for every epsilon greater than 0, we are eventually within epsilon. And what does within epsilon mean? Well, when you're in a normed space, within epsilon means eventually you have the norm of xn minus x is less than epsilon. So we're getting closer and closer. Closer and closer is measured with the norm, and we need the norm to be less than epsilon. In such a case, we write that the limit of xn equals x, or simply xn arrow x. So we don't even write the limit. We just do it all with an arrow. Here's another remark from the textbook. They say that xn going to x in as vectors means that the difference xn minus x, and then you take the norm that converts the vectors into numbers, that goes to 0 in R. So if you know your limits in R very well, then you can sort of translate limits of vectors into limits of numbers where we're looking at the norm of those vectors. Okay, here are 3 properties that they did not prove, but are true. 3 true properties. If you know the definitions very well, and you've taken a course with limits, like calculus or analysis, these are the types of things you should be able to prove. A convergent sequence has a unique limit. So on the face of it, there could be more than one limit, right? We could have xn going to L, we could have xn going to R, and R and L maybe are different. Could that happen? No, it can't. So the limit has to be unique. Another thing is that scalar multiplication and addition will respect limits. So with the definitions the way they are, they will respect the limits. So for example, if you have a sequence of vectors converging to x and a sequence of scalars that are also converging in R, then if you multiply them together, they will converge. So the convergence respects scalar multiplication. Another property is that it respects addition. It respects vector addition. So if xn is converging to x and yn is converging to y, then their sum converges to x plus y. These are absolutely great exercises if you're like, hey, I'm not sure if I'm understanding the definition. Write out what these mean and try to prove them. This is a great example for you to do. And the proof will just be checking all these properties. So you will use the properties of the norm. You'll have the properties of the norm. You have the properties of the vector space. You have the definition of what a limit means. And you will write down what this thing means and then check and make sure that it really works, right? When you do the limit of xn plus yn, why is it true that the limit is x plus y? How can you do it? Let's do some examples. And so here's an example of a norm. So the easiest example is, again, on the easiest vector space, let's say R4, right? So you have vectors with 4 components. The simplest possible norm is the ordinary Euclidean norm. So the norm of some vector x1, x2, x3, x4 will be the sum of the squares x1 squared plus x2 squared plus x3 squared plus x4 squared. And then you take the square root. So this is actually the squared norm. That's the ordinary, like, Pythagoras distance function that you are used to from linear algebra class, and that is a norm. So you must check, it verifies triangle inequality and so on. But this is the kind of thing you can do. Okay. Totally valid norm. Here's another one, again, on my space R to the n, which is the sequence space. This is the set of possible sequences. So let's write them with x's again, x1, x2, x3, ... These are sequences in R. Xi is in R, and I is going from 1 to infinity. You could make a very similar norm. So you can attempt to do the sum from I equals 1 to infinity, the infinite sum, the norm of some sequence of these things will be the infinite sum xi squared, and then you could try to do the square root at the end. And there is a problem which is that when you're doing an infinite sum, the answer might be infinity, and that would not be allowed. So this on its own is not a norm on the full space R to the n. And the reason is because for some sequences, it does not return a finite number. So it's not a norm because the norm of, let's say, as a concrete example, the sequence 1, 1, 1, 1, 1, 1, the sequence that's ones forever, has an infinite norm. So it would be equal to infinity. And that is not allowed. So norms have to be an honest to goodness number. I think that was technically in the definition somewhere. So it maps things into R, not into R plus infinity, just like honest numbers. And so therefore, this is not a norm. However, what you can do is work in a subspace. So this is the way we get around this, is we're going to look at a subspace of R to the n. And this subspace happens to be called little l2, and it's the set of sequences in R to the n. Okay, R to the n, I mean by this natural number n. So sequences, natural number valued sequences, such that the sum is finite. The sum, square root I equals 1 to infinity of xi squared is less than infinity. I guess I don't need the square root. Let's do it like this. Less than infinity. Okay. And so if you look at only the sequences that are whose sum of squares is less than infinity, whose sum of squares is a finite number, it turns out that is a subspace. So this is a subspace. This is a subspace. What do we have to check to make sure this is a subspace? We have to scalar multiply it. If you multiply something where the sum of the entries squared is less than infinity, you multiply by 3. Is it still less than infinity? Yes, it is. Very good. If you add two sequences, would you get something that is less than infinity? That is a little bit trickier. And that goes by, this is done in the textbook, but I won't do it here. So checking sums may be trickier, but actually it's not so hard. Checking sums is needed, let's say. So if you have one sequence whose sum of squares is finite and another sequence whose sum of squares is finite, and then you add together everything, is the sum of the squares of that finite? Okay, again, you would need to check that, but it is true. And so L2 is a subspace of Rn because it is closed under addition and scalar multiplication. And on this space, the norm I said is a total valid thing. It is called the ThTu norm. It is called the ThTu norm. So the norm, this is called the norm sub 2, and this is not a norm on R to the n, but it is a norm. So yes is a norm. Yes is a norm on little l2. So it's a valid norm on sequences as long as you restrict yourself to only looking at ones where things are finite. Again, you would need to prove this, so you need to check the definitions of a norm, and this is done in the textbook under the name of Minkowski's inequality. It's a pretty technical proof. You do not need to know the technical details of the proof for this one, and the hardest thing to prove is the triangle inequality part. So does this infinite sum thing, does it obey triangle inequality? It turns out it does, and proving it is a little bit tricky. Okay, that's it for now. And once again, I will post the specific parts of the textbook that we covered as well. Please let me know if you have any comments about the video.